The specific heat capacity of a gas is the amount of heat required to raise the temperature of 1 mole of a gas to 1 Kelvin is called as specific heat capacity of a gas. So the repetition of a cycle, that is a procedure after a certain interval of time, is called as cyclical process. Then we will have to integrate from volume V1 to V2. We'll have to integrate what is the changes taking place in the work done. Hello everyone, I'm Brinda from Department of Physics, welcoming you all to chapter 12, and the chapter name is Thermodynamics. So today in this chapter, we are dealing with something with respect to temperature. That means thermodynamic effect of this temperature, thermo. So the first of all, we are checking on to the what is meant by thermodynamics. The one which deals with transfer of heat energy from one place to another or its conversions. So suppose if there is a glass of a coffee or a cup of a coffee which is given in a winter, after a certain interval of time, maybe after 5 minutes, its temperature decreases. Why does it decrease? It has to stay along with the liquid, right? But when it is in contact, when the liquid is in contact with the surroundings, what happens? The temperature from the higher temperature region, that means the coffee's temperature, it gets released to the surroundings. So that how much it gets released? Until and unless the outer temperature as well as the inner temperature comes into some consistency. Till then, the heat is released to the surroundings. So all these concepts, what happens when the heat is released, what happens when the heat is intaken, all these concepts we are studying under this chapter called as thermodynamics. So we have the laws to study the thermodynamics. It might be zeroth law, first law, second law. All these are certain set of laws that we have to understand in order to understand the thermodynamic concept. What does your zeroth law states? If there are two systems, one is system A and B, which are separately in thermal equilibrium. That is, there are two systems, system A as well as system B, both are separately in equilibrium. This is in equilibrium, this is in equilibrium with the third system, that is C. If this is equilibrium with C and B is equilibrium with C, then automatically you can tell that A and B are thermally equilibrium with each other. So that is all about your zeroth law of thermodynamics. Suppose if you have a temperature for this system TA and the temperature for this system, call it as TB, and the temperature for this system, call it as TC. Suppose if TA is equal to the temperature of the system C and temperature of system B is equal to temperature of system C, then you can say that temperature of A will also be equal to temperature of B. This is actually your zeroth law of thermodynamics and one of the easiest law. Okay. Next we are having first law of thermodynamics. So let us study what is meant by first law of thermodynamics here. The heat energy which is given to the system, that is heat energy is determined in terms of Q. It will be equal to sum of increase in internal energy. Here in the physical notation, the internal energy is given as U, and the external work done by the system is given as W. So there are the changes taking place. So let us read it again and frame a equation here. The heat energy given to the system, that is dQ, there is a change in heat energy. It is equal to the sum of increase in the internal energy. So there is an increase in internal energy, that is also having a change. So increase in internal energy and work done. Work is being done. That means to say there is a change in work done. So change in work done. So dQ is equal to du plus dw. This equation holds good for your first law of thermodynamics. So always remember your zeroth law as well as the first law. First law you can remember with respect to your equation. Now, applications of first law of thermodynamics, it is what we will see. So first application turns out to be the relationship between Cp and Cv. So what are the Cp and Cvs of gas? It is called as Cp, Cv both are specific heat capacity of gas. And we have studied in thermal properties of matter, what is that specific heat capacity of a gas? So specific heat capacity of a gas is the amount of heat required to raise the temperature of 1 mole of a gas to 1 Kelvin is called as specific heat capacity of a gas, wherein Cp is at constant pressure and Cv is at constant volume. So suppose if you consider 1 mole of a gas at constant volume, your temperature is increased to dT, but the volume is said to be constant, due to which your internal energy also increases, but the work done is said to be 0 here. So according to the equation dQ is equal to du plus dW, we have the work what is done is said to be 0. So dQ is equal to du. Okay, so heat energy whatever is supplied is used in terms of your internal increase in the temperature of the internal energy. So now you know that dQ dash, when the heat is supplied, what happens at constant volume? There is increase in temperature for 1 mole of a gas. There is rise in temperature. So change in temperature is dT. So Cv into 1 mole of a gas, there is rise in temperature can be given as dQ dash is equal to Cv dt. So dQ is nothing but du. So you can even call it as du is equal to Cv dt. So as we know that du is nothing but Cv dt. Now let us check. Same thing we are going to apply in case of your constant pressure. At constant pressure, you have dQ is equal to, you have Cp is the constant pressure for 1 mole of a gas and dt. So change in heat energy is Cp dt. So you have Cv dt for du and dQ is Cp dt. So for this we have got our equation of first law of thermodynamics, dQ is equal to du plus dW. What is dQ? It is Cp dt. And what is du? It is Cv dt. And dW, for dW you can just opt for an equation as work done is equal to force into displacement. So change in work done is equal to force. Force can be equated as pressure is equal to force per unit area. Force is pressure into area. So pressure into area into the displacement. So which is equal to, this can be considered as volume. So we have PV. dW is equal to P as well as V. For the change in volume we can give as P into dV. So what is dW? dW is P into dV. So on application of this, so Cp dt is equal to Cv dt plus P dV is the equation what we get. So in order to apply certain set of value for this, we can take PV is equal to RT, which is also known as ideal gas equation. So on differentiating this point, we have d of PV by dt is equal to d by dt of R and T. So on differentiating this, we can keep so we can just write P into dV by dt is equal to R into dt by dt, turns out to be 1. So P dV is equal to R into dt. We can apply instead of P dV, we can apply R dt. So we have from the equation, let us consider this as equation 1. From equation 1, we have Cp dt is equal to Cv dt plus R into dt. So now taking all dt's out, so it becomes Cp. Let me just take this specific heat capacity at constant volume towards the other side. Cv dt is equal to R into dt. dt cancel. So we have Cp minus Cv is equal to R. This is the relationship between the specific heat capacity, constant pressure as well as constant volume, which is also called as Mayer's equation. Next we are going on to Isothermal process. What happens during isothermal process? That is, there is a change in pressure and volume takes place at constant pressure. Such kind of a process is called as isothermal. The temperature is isolated. Isothermal process. Next, we are going on to adiabatic process. In adiabatic process, the pressure, volume and temperature will change such that heat is neither allowed to leave out of the system or to enter the system. That means heat is said to be constant. dq will be constant at this case. So when dq is equal to constant at this case, your du is plus dw will be the equation. So this turns out to be 0. So du is equal minus du, dw will be equal to minus du. So this condition comes out to be in case of your adiabatic process. Next, we are going on to what is meant by a cyclical process. Cyclical process means once the process has happened, again it happens in another form. Okay, again the cycle repeats every now and then after certain interval of time. So the repetition of a cycle, that is a procedure after certain interval of time, is called as cyclical process. In a cyclical process, the system undergoes series changes and finally it returns. That is always about your cyclical process, wherein you can actually find an example of a Carnot cycles. Okay, so now you have isochoric process, in which the changes which takes place in pressure and temperature, but the volume is said to be constant. Only pressure and temperature changes with respect to volume. Such kind of a process is called as isochoric process. Next is reversible process. In case of reversible process, it's a process in which can be made to go in a reverse direction, so that all changes occurring in the direct process will be occurring exactly reversed again. Okay, and irreversible process is a process wherein we don't get the procedure again. It can't be reversed back. So in case of reversible process, you can even consider a rainwater reversing, that cyclical process. Those concepts also you can actually called as reversible process. But irreversible process are the ones which are like, for example, milk turning into curd. Such kind of a concepts are called as irreversible process. So you need to know that the thermodynamic holds good with respect to this irreversible as well as irreversible process. As you can see here, irreversible process, it's a process which cannot be made to go in the reverse direction. As you know, the sentence or the definition itself, the heading itself tells that it is irreversible. It can't reverse back again. Next is work done in an isothermal process. So isothermal process means a process where the temperature is said to be constant. So there is a conducting cylinder in which 1 mole of a gas is present and which is pushed with the help of a piston. So consider this as a piston in order to push those 1 mole of a gas in a conducting cylinder. So when this is the case, we have to check the work done. Work done is equal to force into displacement. Force is nothing but pressure into area and displacement. So this holds good with respect to P into dV. So W is equal to P dV is your concept. So we know that by our ideal gas equation, we have PV is equal to RT. For N mole of a gas, it turns out to be nRT. So P is nothing but RT divided by V. So let me just substitute this P value in case of equation 1. So we have W is equal to RT divided by V into dV, and since this is a change in work done, we just give it in this form. So let us consider this as equation 2. This is just for 1 mole of a gas or 1 second interval of time, probably like that. So for one single time, we just take this concept. So suppose if we want to consider that the complete work, then we will have to integrate from volume V1 to V2. We'll have to integrate what is the changes taking place in the work done. So which is equal to integration of V1 to V2. dW is nothing but RT divided by V into dV we have, which is equal to W. So R and T are the constant terms because we are checking out with respect to isothermal. Temperature is constant and R is a universal gas constant. and we have to go on only with V1 and V2 of 1 by V. This is limits and 1 by V dV. So W is equal to RT 1 by V can be written as log to the base E into V, and in order to substitute the limits we will have to write along with the brackets. So W is equal to RT, substitution log to the base E V2 minus log to the base E V1. We can even take this as W is equal to R2 log to the base E V2 divided by V1. This is a set of formula. By the formula we get to V2 divided by V1. Suppose if you want to convert log to the base E, it is also called as ln function. Suppose if you want to convert this, then you will have to use 2.303 for value for ln. Multiplying 2.303 log gives you the ln value. So we have W is equal to RT and 2.303 of V2 divided by V1, which can be written as 2.303 RT log. Here we will have to add up log to the base V2 V1. Okay, so this is the set of equation. Suppose if for n mole of a gas, we can write this work done during isothermal processes 2.303 nRT log to the base V2 by V1. This is the final set of equation to the work done. So this is all about your work done in an isothermal process. Next, let us check work done during an adiabatic process. So now during adiabatic process, as we had studied, during adiabatic process, there is no exchange of heat, so dQ will be equal to 0. When you apply the same thing to your first law of thermodynamics, dQ is equal to du plus dW, you get this is a 0. So 0 is equal to du plus dW. So your du is equal to dW. du turns out to be a negative value of, that is minus du. So now you have du value, we know that is Cv dt. When you just apply the specific heat capacity at constant volume of a 1 mole of a gas, you get this equation. So du can also be written as dW. So dW is equal to minus Cv dt is the set of equation what we will have in order to proceed for the work done in adiabatic process. So now, in case of this adiabatic process, the heat is the one which is not exchanged, but there is a temperature from T1 to T2 which varies. So between that limit, we will have to set up this work done. So now, this is the second step. On integrating from temperature T1 to T2, the work done, what exactly it is, integration of T1 to T2, negative of Cv and dt is what you have. So now, integration of dW is W and Cv is the constant one, minus Cv, integration of T1 to T2 into dt turns out to be T itself, so minus Cv of T2 minus T1. Okay, so now we know that Cp minus Cv is equal to R. This equation is that we know condition. Okay, divide this equation completely by Cv. So Cp by Cv minus Cv by Cv is equal to R by Cv. Cp by Cv is gamma notation. Cv by Cv is just 1. So we have gamma minus 1 is equal to R divided by Cv. So having this set of equation, then we can just write Cv is equal to R divided by gamma minus 1. Apply this condition to this one, that is Cv. That is what we have got it here. We can even apply to this. So what happens? W is equal to minus Cv of T2 minus T1 comes out to be W is equal to minus of R divided by gamma minus 1 of T2 minus T1. So on multiplying this negative sign, we get R divided by gamma minus 1 minus T1. So T1 minus T2. So this is the final expression for the work done during the adiabatic process. So this is all about your work done in your adiabatic process. Then what is the second law of thermodynamics? Second law of thermodynamics has given the concept of impossibilities. So one is Clausius statement is given with respect to second law, and another one is Kelvin statement is given with respect to the second impossibilities. So let us check what is Clausius statement and what is Kelvin statement. One is, they have told that it is impossible for a body, which is unaided by a external force, just to exert certain energy such that the temperature the temperature or the heat energy from a lower temperature region to pass through a heat to a higher temperature region. So it is the external forces. Impossible is what they are actually telling. It's impossible for a body which is not aided by an external force. That is why this into mark is there. It is not aided by the external force. For anything to happen, there should be an external force. Here, without the external force, it is impossible in order to produce or to pass the temperature from a lower temperature region to a higher temperature region. Similarly, in case of Kelvin statement, you have that it is impossible for a body to work. Okay, the work done will be negligible, or the work done cannot happen when a body is cooled to the coldest of its surroundings. So that is what your Kelvin statement tells. So in today's class, we have dealt with the chapter thermodynamics. Let us all meet in our next class in an upcoming session. Until then, have a good day. Thank you.